I've been with the Toronto section since '76 and very active on the board, and I helped with this program, putting it together. We're very pleased with the list of speakers that we've had this year and over the past few years, and you might have noticed from the link that this is the 13 in a series focusing on cost savings and what can be done to improve the economics by the use of better lubricants and better tribology. First, it's not shown on our website yet, but on May 10th, we're having a speaker in Varnish. You'll get more details on that, so please put it on your schedule. What's going to be different is our speakers from Vancouver, and so we're going to be starting at 1 o'clock rather than 10 o'clock. So that's 1 o'clock Eastern Standard Time. That's on May 10th, and you'll be sent out details shortly. So today, our speaker we're very pleased to have Rory Duncan with Pall Corporation. He's a project manager of the Americas. He's based down in Northland, Florida, which when I was Googling it is just a bit north of Orlando. Seems like a really good place for anybody who wants a work term or something down there. He's been with Pall now for 9 years. His background is as a mechanical engineer. He went to Curtin University just in Perth, Australia. He's been with Pall now for 9 years. He also has an MBA, and I heard an earlier version of this put on by Pall on the effects of water. I just want to mention one thing on this. If you're not seizing the effect of water, it might be because you're not taking good enough care of your bearings and murdering them for other reasons because of improper lubrication, wrong lubricant, too much, too little, dirt contamination. The standard design life of bearings is based on subsurface initiated fatigue. And to get to that, you have to stop it failing by all the other reasons. And if you want to get that life as well too, you have to control the water content because that accelerates the subsurface initiated fatigue. There's a number of things that Rory's going to be getting into. Rory's been involved in the field of filtration and separation solutions for a number of years now with degrees in mechanical and industrial engineering, and has a wide application knowledge in the contamination control solutions within several industrial markets. And Rory, it's all yours. And with that, everybody please mute if you're not, and your screens. Thank you.
Okay, I'm just going to jump into the presentation here. Thank you everybody for your time today. Yeah, that's okay. So, excellent. So today we're going to be discussing the hidden and in-your fluid. So in-your fluid systems, mentioning, we're going to discuss some of the problems of water with inside of lube and hydraulic systems, and then dig into some of the ways you can actually economically address the problems associated with water in your lube and hydraulic systems. So jumping right into it. Sorry, computer seems to be going through a little bit of a slow spot. All right, so just to recap a little bit, my name's Rory Duncan. So I've been a product manager at Pall Corporation for 8 years now. I have some background in mechanical and industrial engineering, and Pall Corporation, in case you don't know, is a world leader in contamination control solutions. So we deal primarily with fluid systems, and we address multiple applications across many different markets, from power generation, oil and gas, polymers, into the heavy industry, mining, pulp and paper, steel manufacturing, metals production. So many different markets that we address inside of the world of fluid contamination control solutions. We've been doing this for about 70 years, and we have a lot of background knowledge behind many different applications. So if you have a problem, feel free to reach out to myself, and I can definitely get you in touch with some of our senior scientists and experts if you had a problem with your fluid contamination. So jumping right into it, because I know we're running a little bit behind on time here. So where is water and how does it get into a system? So many of you probably look at your bearing systems or look at your lubricant or hydraulic systems and think particulate contamination is the #1 problem that you want to address with things like filtration and contamination control. And it definitely is a large proportion of it, but there is always a problem with the ingress of water. And we'll get into why that's a problem, but even if you go through, you can cover the main addressable part of reducing water ingression just by introducing really active and preventative maintenance regimes within your facilities. So most Most modern facilities have very good planned preventative maintenance regimes that make sure they've got good housekeeping. They don't leave the tops off a reservoir. They make sure they're topping up their reservoirs with new oil rather than oil that's been sitting around for a while, new lubricant fluids. So by doing good housekeeping, you can avoid water to a large extent, but you can pretty much never remove it entirely from a system. And the major reason being is that you've got multiple points of ingression. And because you've got so many different points of ingression, as listed here on the left-hand side, it is generally difficult to troubleshoot exactly where the water is coming in from. And it can take you a number of, it can take a quite large study to really drill down into this is the exact point of water ingression. So we do advertise, and whenever we send people into a facility, that Pall associate will go in there and do a housekeeping check to begin with. They'll make sure that all the general preventative maintenance practices are being upkept before they start looking at solutions and how to address the actual water side of things. I just think that's important from a really early on topic to just say good housekeeping. That'll get you a long way. That'll go a long way in a very cost-effective manner before you start talking about oil dehydrators and desiccant filters and these kinds of things that can help to solve the problem after it's already occurred. So just jumping in a little bit more detail, and the reason why you do have to start talking about oil dehydrators is because there is just so many points of ingress of water. Very similar to particulate contamination, but it generally is a little more underscored. It happens a little more in the background that people don't really sort of understand or are acknowledged to. So one of the big ones that you get is condensation from humid air. So if you have an open top reservoir, or you have just a reservoir with a gooseneck air inlet for it, so a gooseneck breather, then what could happen is if you have a very humid environment around your reservoir, which is pretty par for the course for many of our steel mills or many of the pulp and paper plants, they're very humid environments, generally a pretty hot area, you can actually get a lot of that air with a lot of water vapor in it getting sucked into the reservoir. That will then just cause that water essentially to sit in the reservoir. It can condense overnight once the machinery is being turned off, and then it can fall into the oil pretty quickly. Other areas are things like makeup oil, where you've had a canister just sitting around, and then it's been able to breathe that open humid air in itself, and you go and top up your reservoir with that water that oil that's now contaminated with water. And even if you've got really good housekeeping practices and you avoid all of these situations, it's still difficult to avoid some of the things like cylinder rods. Maybe the seal on the cylinder rod is slightly failing, and so there's little bits of water that are coming in every time that cylinder rod moves backwards and forwards, or some of the valving might be collecting water at certain points. And so there's multiple different areas where you'll get water ingression with inside of a system. So you can get most of the way there with good housekeeping, but we highly recommend that you implement a good water monitoring practice. And we'll go into that in a few slides time, but then also a good proactive way to address water once it's entered into your system. So you monitor it. Once you identify that water has been ingressed into your system, then what do you do about it? How do you address it? So looking at a paper machine, so just a really pragmatic example of why it can be difficult to completely avoid the ingression of water. So if we look at a paper machine, it has a number of these steam drums on them. These steam drums have the paper residing on the outside of it, and they're supported by two large bearings on either end of the drum. This drum has steam injected into the middle of it to heat it up. And so if there is a small failure of the seal on any one of these number of drums, and these can have up to 50 drums in a large paper machine, if there's a failure at any one of these seals, you can get some leakage going over into your bearings, main lube. And because all these bearings are connected to a central lube system, that will just affect your entire lubricant system, and therefore affecting all the bearings together. So one point of failure on the steam side can then cause multiple points of failure for the bearings, for the bearing lube oil. And it's very difficult to root cause this, and it can happen it can happen fairly spontaneously at these sites on these applications. And it's very difficult to kind of stop it from happening altogether. So having a good way of monitoring when it happens, and then a good system in place to effectively fix the problem once it's happened, is really it's a good situation to be in, because it's difficult to completely avoid this instance altogether. So it's just one example of where it could be difficult to completely take out the problem of water getting into your oil system. So water contamination in oil, why is this a problem? And really, what does it do, and how does it affect you in a detrimental way, and how does it cost you money, essentially, for your facilities? So if we look at the top, and you're probably more than aware of where I'm going with this, but just to help sort of frame up the conversation for the rest of the presentation here, a study was done back in the 1970s to look at the loss of usefulness of machinery. So it looked at if you had a piece of machinery and it was running at 100% productivity, what was going to cause that machine to lose its productivity, slow down, increase its heat, increase its internal heat output from friction, therefore needing more energy input. All these different factors were put into this study to look at this idea of usefulness for this piece of equipment. And they found that there was some accidents, so improper use of the equipment and obsolescence of the machinery essentially voided the usefulness. But they were the smaller parts. The big section of loss of usefulness, and it's really why filtration and contamination control is such an important part of machinery protection and machinery essentially longevity, is surface degradation. And so this study really focused in on surface degradation was the primary reason why pieces of equipment lost their usefulness and their productivity throughout their life. And it was found that 20%, overall 20%, was caused by corrosion. And so one of the major reasons why you want to take out oil at the beginning is to avoid this corrosion aspect. Corrosion has can derive in a couple of different ways, primarily water and air. Once you've got those two mixed together with a metal surface, you're going to start to get rust and corrosion breakdown in your system. And that will then cause some further problems, such as the generation of rust particles, and that will then create mechanical wear. And then mechanical wear will start to further degrade the surface and further break down some of your downstream equipment, such as gear pumps and some of your valving. That could then be very costly for your overall system. But just at a very high level, this loss of usefulness, if you think of it in terms of productivity, that equipment, if you have water in your system, you're potentially, over the lifetime of that piece of equipment, losing 20% of its productivity. And so that's 20% pretty much hits straight to that top line revenue that you're pulling out of that piece of equipment. So it really does add up after a while. So if you can address this, you can get a massive bump in productivity overall from your equipment. And just a little look at what the difference between dry and saturated water and saturated oil with water looks like. It's fairly stark, the differences between the two samples here. So you can tell when water has affected oil very quickly. It has a relatively large effect just looking at the corrosion aspect of it. So just looking at a couple of the pictures, so you can see that these pipes were essentially half filled. So the top half had an air pocket in them, and then the bottom half had the oil. And then because the top half had that air pocket in it, and there was water vapor that was mixing around in this area, you started to get rust particles generating fairly quickly. And that rusting on the surface will then generate further particles, creating further wear, and then it just creates this cycle of wear within the entire system altogether. And now, not just only do you have a water problem, you've got a filtration particulate problem, and then that might also generate into a further issue with your equipment essentially needing more power to run because now it's got more friction in the system, or you need to essentially failure of that piece of equipment, you need to replace it. So it can cause some really big downstream effects if you let it get this bad. This is a very bad example. So your systems probably aren't, if you do have air pockets in with oil, this was a sort of extreme example, but it is not uncommon to see rust build up inside of reservoirs, inside of lubricant hard pipes. So just that could be going on inside of your system. So if we also think about the detrimental effects of water, you can think of it in two different ways. One of them is that corrosion way that we discussed, but there is a second area which is just as important, and it doesn't quite affect the usefulness of equipment, but in the way that that original study was looking at it, it more affects it in terms of how the overall system is doing its job, and kind of how are you producing paper or steel, or how is your mining equipment performing overall. And what essentially the second study that Paul performed was looking at these high molecular weight compounds. What was generating varnish and sludge within inside of these systems? And I'm glad that Ken actually mentioned that the next session is one on varnish, because varnish is not a very well known property or contaminant within inside of many of these oil systems, but it can have some massive detrimental effects on your overall equipment. And so do actually go listen to that second, the next session, because you'll learn a lot about how varnish can actually, it can essentially take out your filtration system and then destroy your piece of equipment straight after it very, very quickly. And the precursors that generate into it happen very fast. You can go from having a pretty clean system to having a very highly contaminated varnish system very quickly. So it's something that you really want to watch out for, and it's difficult to monitor in terms of taking samples. You have to actually ask them to look for some of the precursors. That was a little bit of a side story there, but what we're trying to explain here on this slide is that when they looked at what was generating these varnishes and sludges, they went back to, okay, how do these get developed? And the precursors to them are things like these ketones and carboxylic acids, alcohols. And so these ketones and carboxylic acids were really the molecules that started that polymerization reaction that caused varnishes and sludges. And so where did these alcohols and ketones and carboxylic acids come from? And they found out that not only was it generated by the water, but if you had a metal catalyst in there as well, that would then further, essentially it would create a catalyst for the greater generation of these precursors to varnish. So it would really ramp up the production of them, and then that would cause varnish and sludges later on. And then you would need some oxygen to mix in there as well to really help the reaction start to take place. So if you look on the left-hand side here, what this chart is meant to show you is on the final neutralization number. If you look at that number, the higher that number is, the faster the generation of precursors to varnish are generated. So the higher the number, the more of these precursor molecules are generated. And so you can see that whenever there's a metal catalyst as well as water at the same time, it has a much larger effect on the generation of these precursors. And these precursors cause varnish, which has some very, very detrimental effects overall, but it can also cause things like fatty acid chains to develop. And fatty acid chains essentially help to break down oil, and they can cause lower lubricity. They can cause some other problems with oxidization within the oil. And because of this oxidization, loss of lubricity, you can then cause greater amounts of machine wear, which creates particles. And then it's sort of that vicious cycle all over again. The more particles that are in the system, the more catalysts that you have mixing with that water, and therefore you get more generation of these precursors. And then it can essentially keep going like that until you have some kind of great failure. So if you can take out this water, you can really reduce any effect of this happening, because then essentially it doesn't matter how much catalyst is in there, doesn't matter how much metal particulates are in the system, the water's not there for it to essentially enable the reaction, and therefore you can heavily prevent these precursors to varnish and sludge. So removing water can help really sort of eliminate varnish from being a problem in your system, and a lot of these high molecular weight compounds. So just something to think about, that removing the catalyst might not always be the easy approach. It might actually be easier to just remove the water. You'll get a much more effective solution for addressing varnish. Some detrimental impacts. This is just a look at some pictures to show you all the areas in which in which water can be detrimental for your systems and for metal surfaces. So we've got some galvanic corrosion. So this is just etching where the metal's being peeled off the surface. We've got some spalling on a bearing race. And one of the other things that I should mention is that the things that are in the water, normally when water gets mixed in with your lube system, it's not reverse osmosis pure water. It is normally just water from the air or water from a tap source. And so it has particulates and probably some ions in it. And those will react or have the propensity to react with potentially some of the additive packages or to react with the oil itself. And so by ingressing some of this sort of contaminated water, you could say, now you can precipitate out some of your additive packages because it will react, causing it to essentially just drop out. Now you've lost your additive package for your oil. So whatever that was put into the oil to do, it might not be able to perform at the specification that the supplier of that additive package wanted it to perform at. And so this is a really sort of ancillary area, but it's also of importance because people are looking at their oil and thinking, why am I getting foaming? Why is this foaming problem happening? And they don't think, oh, maybe the water that's been ingested into my reservoir has caused a reaction with my foaming agent, dropping that out of solution, dropping it out of the oil solution, and therefore I've got no anti-foam in my oil anymore. And that's causing a massive foaming issue for me. So there's a couple of these instances that do occur with inside oil systems. So sort of just to summarize those last couple of slides, when you're looking at the relative life expectancy, and this study was looking at roller bearings, but it's pretty generalized across a lot of different reciprocating or rolling pieces of equipment. You can think of it in terms of life expectancy on this y-axis. When you start increasing water content, it does have a detrimental effect, similar in the way that particulate size and particulate particle size distribution has a similar effect as to what the water content does for life expectancy of roller bearings. So we've seen this in a number of different pieces of equipment where as you increase that water content, you start to get dangerous corrosion, you start to increase the oxidization of your lubricant hydraulic systems, and that will then reduce the performance of those lubricant hydraulic oils, and therefore you'll start to get this loss of life of the equipment pretty quickly. So it is a fairly dramatic drop that you start to see as water content starts to build up. So it does have a fairly big effect overall. So oil content, just to kind of summarize again, so fluid breakdown, what does water do inside of oil systems? So number one, fluid breakdown, so additive precipitation and oxidization, that's a big problem because it means that your oil isn't performing how you wanted it to perform. Reduced lubricating thickness because oil has much lower hydrostatic film thickness of it, and once it starts mixing with that oil, now you reduce your film thickness overall, then you start to get some contact between those two mating surfaces. That'll then generate particulate wear, greater amounts of particulate wear, and then you've got a filtration problem to deal with. Accelerated metal surface fatigue, as I mentioned, you've got some of this corrosion aspects. Yeah, it will accelerate any crack propagation because it starts to move into those cracks. And then loss of dielectric strength in insulating fluids. This is something we haven't mentioned. It's very specific for the power generation space, but if you're using your oil as an insulating fluid, once water gets in there, now that insulating effect starts to reduce and it can become a little more dangerous to use that oil as an insulating fluid. So loss of dielectric strength is important for those insulating oils. So equipment failure, and all this essentially leads to equipment failures, production losses, operating inefficiencies, high fluid disposal costs, and a list of many more different problems that you can face. And at this point, you're probably thinking, so we just need to remove all water from our systems. And that's the best case scenario, but economically, it's generally not an achievable goal. You'll have to put in very large dehydration systems in your facilities to remove all the water. And so what a lot of people advertise is you should try to balance that economic scale versus the damaging effects of water against each other, so that you're economically essentially acting on when water gets introduced into your system. And to explain this in a little more detail, we can kind of look at, well, what types of water in oil have the greatest effect. And so if you look at the picture just to the right hand side here, we've got three different measuring cylinders. And on the far left, we have a measuring cylinder that has dissolved water in it. The middle one has emulsified water in it. And the right one has a split between free water. So you can see the free water build up at the bottom. You can see some emulsified water at the top. So it actually has free water present. So we're going to go into what that is and how we can address those three different types of water being present in our oil reservoirs. So just from the outset, so free water is really the most damaging piece of all of this. Free water creates a number of additional problems, such as the generation of bacteria inside of your oil systems. So at the surface between the water layer and the oil layer, you can actually have and if you get a microbe into your system, you can actually live in between the interface there and start to generate and grow into this very sludgy type of tar material, which can do essentially very similar effects to what varnish does to your system. And so you really want to avoid free water at all costs. So everything should be put into completely avoiding free water. The good thing is housekeeping addresses free water very, very well. So if you have good housekeeping practices, you maintain closed reservoirs, you have desiccant breathers on your reservoirs to avoid any humid air getting into them. You make sure you top up with clean oil, clean new oil. Then you should be able to address a large proportion of free water within inside of your system. Of course, there's always mistakes that happen, and so you may still see free water, but overall, that's what you want to address primarily. Once we start talking about the saturation point of water in oil, and we start looking at the dissolved area, this is where you start getting all those problems that we've previously just mentioned. So the dissolved water has some very detrimental effects that we've mentioned previously. It's not as bad as free water, because free water is literally just straight water in your system. It's not dissolved within inside the oil. It's not like you have this mixture of oil and water present at the same time. It's just water hitting your pump. And so you have some really bad effects with that. Whereas with dissolved water, it is mixed in with it, so it's slightly dampened the effect of what water would do, but it is still detrimental overall. And so you want to reduce your dissolved water number as much as you can in the most economic sense possible. There is several different pieces of equipment that can do this, and we'll go through some of those pieces of equipment in a couple of slides' time, but that's really the goal here. Free water, take that out completely and reduce your dissolved oil number as much as possible. So what is dissolved water versus free water, and what parameters do you need to look at in order to measure it? So if we look at the curve here on the right-hand side of the slide, you can see this is a saturation curve for oil. You get your oil supplier will be able to provide this for you for basically whatever oil you purchase from them. So if you don't have this particular piece of information, do ring up your oil supplier and ask them to provide you with their oil saturation curve for water. And what the information this will give you, if you're running your equipment at 50 degrees C or 122 Fahrenheit, then that means the saturation point, so where you'll start to go from having free water to dissolved water, that line at 100% saturation will occur at about, for this specific example that you see on the slide, will happen at about 110 ppm. So your saturation point will be 110 ppm of water, and then anything above that is going to be free water that is just existing in your system. And so you want to make sure that you're at least below 110 ppm at 50 degrees C. So that's really the critical piece here, is that. And you can probably see it from the slide. As you start to decrease temperature, that saturation point goes down. And as you increase temperature, that saturation point will increase to higher and higher amounts. The oil will essentially be able to, more water will be able to dissolve into the oil. And so at higher temperatures, and less will be able to dissolve at lower temperatures. So it's important to not just measure the amount of water, but also the temperature at which that measurement is being taken, so that you know where you are on this saturation curve. Because if you're just measuring 100 ppm water and you could be at 25 degrees C, then you're well into the free water category. And so you've got all these detrimental effects of free water affecting your overall system. But if you're at the 50 degrees C area, then you should be okay. So, well, not okay, but you won't have those detrimental effects of free water. You'll just have to address the dissolved water. So how do we actually measure this? And there's many different ways of measuring water. And so if we look at so some of the easier ones, the crackle test, this is a very old school method of measuring water and oil. It's not quantitative, so it's a qualitative solution for measuring it. Essentially, you're getting a sample inside of some kind of metal cylinder, and you're heating that sample up, and you're seeing if the water essentially starts to crackle or evaporate off from the oil sample, similar to like deep frying, if you think of it that way. So not a great method for an industrial solution. Chemical, you can add, you can put additives into a sample. Those additives will then mix with the sample, and you can do things like titrations, or you can do precipitates, and you measure the precipitate, and that will tell you how much water is in there. Again, it's not very accurate. It takes time as well, and there is a number of different reagents that you need to continually purchase in order to do this effectively. So it's a good method for a laboratory scale, not really for an industrial scale. The rest can be much more effective for larger industrial scales. So distillation, limited accuracy again, and it can also be affected by it can also not really be the best method for determining where the water is coming from. FTIR, so Fourier transforms, they again, you've got to buy very expensive pieces of equipment, so you might not have that piece of equipment readily available to you, so you have to send it out to a lab anyway. So again, this could be maybe not the best way, and it's not as accurate for low water concentrations. It's really accurate for a higher level of water concentrations. Carl Fisher is the laboratory method for measuring total water. So it will give you a very accurate measurement of total water within your system, so both your free water and your dissolved water. However, once you start getting very low amounts, it tends to get more inaccurate. And again, it is a laboratory test, so you would need to have an established laboratory at your facility or send it out. So the one that we advertise at Pall Corporation as being the best method for measuring dissolved water is capacitive sensing. So you can put these online in your system, and then they will measure between 0 and 100% saturation on a linear scale, very accurate between the 0 to 100% saturation point. The biggest problem that we get with, there's two problems with capacitive sensors. The first one being they don't measure free water, so it will just read 100% saturation, so you'll never know the total amount of water in your system. This isn't necessarily too big of a problem because you can address that free water. You have to address that anyway. So if you're at 100% saturation, you know you've got a problem. You don't really need to measure it anymore at that situation. You just need to address it. It's kind of just go out and do it. You don't really need to know how much is in there because you have a real problem. The other issue is that if you want to measure it in ppm instead of percent saturation, you do need to essentially put in a number of parameters into a piece of software that is attached to the capacitive sensor so that it knows the saturation curve. The saturation curve is different for almost every oil, and so because of how they manufacture the oils, so you can get different curve gradients, and so because of those different curve gradients, then you need specific parameters and constraints in order to transfer from percent saturation to ppm. So generally, we advertise you should measure it in percent saturation, but a lot of people, their liability manuals are written in ppm, and that essentially causes them from some frustration when using capacitive sensors because it's more difficult to measure it in ppm than it is to measure in percent saturation. So these are just two examples of some capacitive sensors that you will see on the market. So the WS12, WS18. So these two units can measure in ppm and percent saturation. So you can put them directly in line. They can also do some tracking and monitoring, trending with some other devices that can be attached to them. So once you've measured that you have water in your system, what do you do about it? So at the beginning, and when if you've just got free water, we can use things like coalescers, we can use absorption filters, we can use centrifuges. But generally, so once you take out all the free water, then you start moving into more and more difficult areas of it becomes harder and harder to remove that water. And so the number of technologies available to you starts to limit down pretty quickly. So if we look at just it's a good piece of equipment. It takes out a lot of the water very quickly, which is a centrifuge. But again, it only really addresses that free water level. You can, of course, do things like put a heat exchanger before your centrifuge, drop that temperature down, drops you down further in the saturation curve, and therefore you can take out more water. But you're just increasing the number of pieces of equipment. It could be fairly complex. There can be some other problems overall with using centrifuges. They are a moving piece of equipment, so they're a rotating piece of equipment, so they have their own maintenance problems involved with it. Overall, they're very good at actually removing free water, and they do a very fast job at removing free water, but they are unable to address dissolved water, and they might not be the most economical solution overall. Coalescers are similar to a filter element. So essentially you're grouping together small water droplets into larger water droplets and then separating them out from solution. It's a fully mechanical process, so it's kind of like squeezing water droplets together. And that squeezing action means that it's only affecting free water. You're not really, and it does go into the emulsified water area, but you're generally not touching any of the dissolved water at all with a coalescer. And you can also get some problems with disarming, where if you have some surfactants, which are pretty common inside of lubricant and hydraulic systems, those surfactants will blind off coalescers fairly quickly, essentially making them useless and reducing their lifetime from years down into weeks in some instances. So there is some major problems with coalescers being used for hydraulic and lubricant oils to remove free water. And again, they do not address any of that dissolved water area. Absorbent materials, you can get a little bit into the dissolved water with absorbent medias, not very much though. So again, it's really focused on that free and emulsified water. There can be some big problems with once it's reached its capacity of water that it's taken out. Now it can actually start to break down because it's got so much pressure. There's a large pressure differential between upstream and downstream of these absorbent medias. You can start to get unloading of the water, and that unloading isn't just in small droplets, it's in big large slugs of water can go downstream. We generally at Pall advertise not to use absorbent medias for that reason, because they can cause some much larger problems. Oh, sorry, disarming. Let me just jump back. So disarming essentially is when a media surface gets coated with surfactants, and those surfactants will essentially bond to the media surface. And then if a water droplet tries to connect onto that media to perform coalescence, it'll actually bounce off it. And so coalescence, it disarms is what we call it at Pall. It disarms the media. It stops the media from being able to coalesce actively. That's a good question though. We have if you're interested, do reach out to me. We have a whole technical presentation on coalescence. It's very useful for separating out free water. So if you really want to address free water quickly, coalescers are quite a good technology. Not that great for hydraulic and lubricant systems though, for some of the reasons I mentioned. They're not the right technology generally. And then, so removing free water might not be enough. So and I've explained this a little bit in a previous slide, but imagine you're at this low cool temperature point, and no, sorry, imagine you're at the high temperature point, and you remove all of your free water. So you're using a centrifuge. A centrifuge is a really good piece of equipment at removing free water. It removes all of the free water from the system, and now you're at this second point here. You're right on the saturation curve, and then your oil goes through just a pipe that isn't insulated. You're in Canada, and it's negative 20 degrees outside, and it dips down a little bit. I'm just making up a situation here, but just if your temperature dips down a little bit, then what's going to happen is you could actually move down into an area where now you have free water because your temperature has reduced, but the amount of water content in your system hasn't. So you can actually go from this second point to this point number 5, and now you've got all this free water in your system. And that free water can then remain in the system until essentially it gets redissolved back into the oil, but it can, as it's going along as free water, can cause all those damaging effects. So potentially just removing all of the free water will generally not be enough. You do want to get it down to the point at which you're under your saturation curve for the largest temperature range that you're dealing with at your site. So don't just cool it down. Don't just remove the water that you think you have at one point. Try to look at your entire temperature range that you deal with. And economically, of course, you can't get down to really low temperatures, but economically look at the widest temperature range that you have and try to get down to below the saturation curve at your coolest point. So it's really important to look at your coolest point that you're dealing with. So the last piece of technology we're going to cover here is vacuum dehydration, and this is really the big piece of equipment that's used to remove a lot of the dissolved water. So if you have dissolved water in the system, vacuum dehydration technology is the premier. It's the #1 technology for essentially removing all of that dissolved water from the system. Many different ways of doing this, and so the one way you see on the screen here is actually a nozzle technology. So what's going on is fluid, contaminated oil, it's contaminated with water, it's coming in through the inlet on the left-hand side here. It's moving through a filter, so just to make sure that you don't get any particulate inside of the vessel, the dehydration chamber here. And then the oil will actually fan out from the nozzle into a very large, high surface area, thin film fan of oil that's spraying down into the collection zone at the bottom of the vacuum chamber. So the reason you want a large surface area, the more surface area there is, the more water that can be driven off. It's a key feature of many dehydrators is how much surface area they can produce. So it's an important piece that a lot of manufacturers try to promote. And so with the nozzle technology, you're pretty limited with the surface area that you can produce. There's another technology that I'll show you on a further slide, which uses essentially a number of randomly located rings, and the oil gets dripped over those randomly located rings, creating a much larger surface. And so you can get a lot more water removed because there's more surface area of oil to essentially remove that water from. And so what's going on is that you create a vacuum in the top of the chamber, and that vacuum will essentially dry out. You can think of it like boiling off, but it's not boiling. It's essentially creating a lower than atmosphere environment for the water. And so the water wants to go into vapor form instead of being dissolved in the oil. And because it wants to go into vapor form, it turns into vapor, then gets sucked away through the vacuum pump out the top of the vessel. And so the last slide, so not the last slide, but one of the last technologies that we'll cover here, it's a dehydrator, but this system uses those randomly located rings that are all interlocked with one another. And this is the system that Pall promotes. So I won't cover it for too much, but it removes 100% of free water and gas at the same time. So it's got some gas removal properties to it as well, and up to 80% of dissolved water and gases within inside of a system as well. So it's similar technology to the one we showed on the last slide, but utilizing a different way in which the surface area is built up. So how to select the correct technology, and I've kind of cut to the chase here as we moved through it, but if you're dealing with free water, then you can use things like absorbents, absorbent elements, coalescers, and centrifuges. Centrifuges are a really good technology for free water, but generally that isn't the only thing you need to remove. And so really the main technology that we try to steer people towards is vacuum dehydration, because it just has, it's very effective from both a cost aspect. You have one unit all by itself that has very low maintenance to it, and it essentially can address all of your water concerns in one go. So you don't have to use multiple technologies, you don't have to use any kind of heating or cooling systems with it, and it can address both free and dissolved water. So if we've got a little slide here for two of the major Pall technologies, coalescers and oil purifiers, and you can see that really oil purifiers are the big one that we use to address dissolved water. So it's we would suggest moving for oil purifiers are another name for vacuum dehydration units. So vacuum dehydrators really the premier technology. One additional piece of information to note before we stop pretty soon is there is a new standard out there. It was made in 2017, but it's only recently been introduced to for broader adoption across markets, which is the Dehydration Performance Standard. So if you want to write down ISO 18237:2017, this standard is, so what a lot of the manufacturers had a problem with is measuring their own performance, because they had internal tests. And so Pall had an internal test for our unit. Many of our competitors had their own tests, and none of the tests matched up. They were all measuring different ways of claiming performance. And so when a customer came to us and said, well, this unit has this performance, and we would say, and we have this performance, it was very hard to match those two together. And that's why this standard was essentially invented to try and match all of the performances across all the different manufacturers of oil dehydration units. And so if you want to download the standard, it's it's about a 12-page document. So we also have a white paper that breaks down the standard. If you're interested, just reach out to myself and I can send you a short 1.5-page white paper about the standard and what it actually can do for you. Overall, it'll tell you how fast you can remove your free and dissolved water from your system. So it's a 3-part code. So the first part looks at the dissolved water, and the next 2 parts look at how fast you can get from a high amount of dissolved water to a very, very low amount of dissolved water. So it's just essentially how many passes do I need through my dehydrator in order to get out a certain amount of water. So a good thing to look into is this standard. Last piece, case study. I won't dwell on it because I know we're already a little bit over time and I want to open it up for questions, but essentially Pall went out to a customer in Iowa and we were able to achieve a 15% energy reduction on their system through the installation of three oil dehydrators. So these 3 oil dehydrators solved a number of the problems that were mentioned previously in the presentation, and that then gave them a large boost to their energy output that they already had. So it helped them reduce their energy costs. All right. Thank you very much for your time, everybody. I just want to open it up for any questions or comments.
Well, Rory, it's Peter here. Thank you very much for a very interesting presentation. I'm just jumping in. I don't see any more questions on the chat. If there are questions from the audience, please go ahead now. You can unmute and ask a question if you have one. One question comes up here on the chat, Rory. For the paper mill, how did removing water save energy?
Yeah, so it was friction, I believe, that so essentially they were having a massive amount of wear on their systems, and so all their bearings were starting to they were taking more energy in order to turn their I can't remember the exact application this was on, but I remember that the friction on the bearings was the problem. And so the friction was being caused by a large amount of water contamination, reducing the lubricity, greatly reducing the lubricity. So they had a lot of contacting wear between the bearing and the race. And so that then caused a whole bunch of heat generation and problems. And they had a massive goal to reduce their overall energy consumption. And they saw that as being a pretty easy target because it also fixed their maintenance problem. And so this was a fairly cheap option overall for them because they got a huge hit to energy reduction and they got a maintenance saving.
All right, thank you very much for that. There is another unanswered question, I think, from Ken. For the slide on water measurement methods, what is meant by low water concentration when we look at the FTIR method, for example?
So the FTIR method, not accurate for low water concentrations. So when we start to look at lower ppm amounts, then FTIR starts to, you get too much interference from your other frequencies when you're looking at your frequency response plot. And because of that, it's harder to determine if it's water or if it's an acid chain that's in there, or potentially an alcohol that's being produced or a ketone that's being produced in there that have similar, not exactly the same molecular weights, they're much heavier, but they can pop up in similar kind of peaks. And so it's harder to determine when you have a small amount of concentration.
Okay, thanks, Rory. I don't see any other questions. If someone in the audience still has questions afterwards, please send us an email. With that, I would like to end this presentation. Thank you all for your attendance. Ken, do you have something that you would like to share before we stop the recording?
Maybe just remind everybody about the May 10th one on varnish with Peter Thiessen from Class on Advanced Filtration. I think these are both very, very appropriate. And I guess as mentioned in the Pall presentation, water can also affects additives and does other things as well too, and can lead to varnish. That's certainly something I wasn't aware of. So, for me, that was a great, lesson learned. So again, we'd just like to thank Rory very much for his presentation, and thanks for you as attended. And again, sorry for the bit of the screw up on the link, but it is recorded and it will be on the website. So that's it for me.
Thank you, Ken. And with that, I will stop the recording. Thanks, Rory, and everybody for attending. And you all have a nice day.
Thank you.